Now let's talk about Laplace approximation. Again, we try to approximate the posterior distribution with a normal distribution. And we need to find parameters of this normal distribution, the mean and the variance. So let's talk about how to find those. Let's consider an integral. An integral, it's a definite integral between a and b. And we integrate exponenta of m times h of x. And h of x, we assume, has a global minima, which is quite a strong assumption. But so that's our x, h of x, and we assume that global minima is somewhere at value x 0. And we also assume that h of x is twice differentiable, so we can calculate the second derivative of it. And now let's look at the ratio. So we'll introduce a new notation. F of x is just this exponent of m times h of x, and we will look at the ratio of f of x 0 and f of x. And what you can see, essentially, this parameter m plays a role of something like 1 over the variance. So the larger this parameter m, the more concentrated this function becomes at around this value of x0. So this ratio will have a highest value when x equals to x0. So when x equals to x0, remember, function achieves the maxima. And so when x equals to 0, so that's, this ratio will have a largest value. And essentially m will tell us how much this ratio will change. Now let's do Taylor's approximation of the function h of x at around the maximum, x0. And we will do Taylor's approximation up to the second order. And then we have this residual, the errors associated with the third order derivatives and higher. And since x of 0 is maxima, it's also a stationary point, meaning that the first derivative of h at this value is 0. So we can remove this part of the Taylor series. And at the end, we have this h of x0 and h of x, second derivative at x0 times x minus x0 squared. Now, if you look at, if you plug this in back, h of x, to this integral that we're trying to calculate, so you have this exponent of m times h of x, and we're going to plug our Taylor's approximation. So, and instead of having an integral, we're going to have an approximation of the integral by plugging them to here. H of x0 is a constant, so it goes out of the integral, and inside the integral we have something like this. And if you remember the density function of a normal distribution, you actually recognize that it's almost like a density function of normal distribution. And what we have here, this is our center of the distribution, and in the normal distribution we have this one divided by sigma. So essentially this is 1 over sigma value. And this integral we can calculate. We have an analytical solution to that. So that's the analytical solution when we integrate from minus infinity to infinity, so the whole range. And now if you have a more general function, you want to approximate the integral over g of x, then you just let h of x to be log of g of x, and so integral of g of x is going to be equal to the integral of the exponenta of the h of x, and then still you can have a theoretical solution. Essentially what we are trying to do, we say, okay, we have this some function h. Okay, so it may be something like this. So it's not necessarily a nicely looking bell curve function. And then we say, okay, we approximate it. We try to find the maxima. We call it x0. And then we try to find the variance. And we find the normal function, normal density, that fits this one as close as possible. So that's our normal approximation. And that's our original function. And to find this normal approximation, we need to find a couple of things. So we need to find this x0, and x0 again is just the peak of the original function. And we can find it by using an optimization method. So we just have to find the maxima. And then the next thing we need to find the variance of the width, and the variance is actually, you can see it can be found from the second derivative. So second derivative value calculated at h0 gives us a way to calculate the variance. So we have our mean, we have the variance, so we have the normal approximation, and we're just gonna use that. And once we have that, we can calculate the posterior expectations. And here's a very simple example. So we have a Poisson likelihood. So that's our likelihood. So we have a Poisson distribution, means the variable y takes integer values, and we have the gamma distribution prior. And in this case, this is a case of conjugacy, so we have a conjugate solution. We can analytically calculate the posterior, but we pretend for a second that we cannot. And we're going to use the Laplace, we're going to use the normal approximation. So that's the true posterior. That's the true posterior. We can analytically calculate it. And that's the prior function. And here is how the Laplace approximation looks like. The red curve is our Laplace approximation, so approximate with normal, and that's the true one. And in this case, actually, we can see that it gives us a relatively good approximation.